My name is Hana Sabina binti Muhammad Fiza and my student number is A195555. I will start by introducing Group 24 members, which consist of me, myself, Ifa Hanisha, Muhammad Irham, as well as Hishamuddin. Our CFD simulation project title is Analysis of Orifice Opening Diameter to the Flow Behavior in a Hydraulic Braking System. Our group is supervised by Dr. Wan Muhammad Faizal. To begin with, hydraulic braking systems use fluid to transmit braking force. Thus, it is of utter importance to control the flow of the hydraulic fluid to ensure efficient and responsive braking. Orifices are used to regulate and measure flow, but in the case of hydraulic braking system, it is used to regulate pressure and flow velocity within the brake lines. Incorrect sizings of orifice size may lead to unstable braking. This means that lack of detailed understanding of how the orifice opening diameter directly affects flow behavior can result in poor performance of the braking system. Therefore, this study aims to analyze the effects of varying orifice opening diameters on the flow behavior within the brake lines using CFD simulation. Using the SMART approach, we aim to achieve 5 objectives of our CFD simulation project. First is to analyze the effects of various orifice opening diameters on flow velocity and pressure distribution in the brake lines of a hydraulic braking system. Second is to quantify changes in flow velocity and pressure using CFD simulation results. Next is to conduct simulations of orifice in CFD with predefined boundary conditions and obtain the optimal range of diameters of the orifice opening. Fourth is to ensure better understanding of orifice opening diameter sizing in the design of hydraulic braking systems. And lastly is to collect necessary findings and analyze the effects of varying orifice opening diameter using CFD within the given time frame. Furthermore, it is hypothesized that with varying orifice opening diameter, the flow will also change. That is, when the orifice opening diameter is smaller, the pressure increases and flow velocity decreases. As such, if orifice opening diameter is larger, the pressure decreases and flow velocity increases. Next, I will explain the methodology of our CFD simulation project in the form of a flowchart. Firstly, the geometry of our model is based on a simple straight line pipe consisting of the inlet and orifice at the center as well as the outlet. The orifice is modeled as a circular constriction. To simplify the simulation, we maintain the pipe's dimension as constant with a length of 250 mm, inner diameter of 4 mm, and the thickness of the orifice is 1.25 mm. This geometry is designed using the ANSYS design modeler. It is then imported to ANSYS Workbench in .agdp file format since it is directly linked to ANSYS Fluent. Next, an unstructured tetrahedral mesh was generated to the model using ANSYS meshing tool with default element size of 0.0125 meter. A custom hydraulic fluid was also defined in ANSYS Fluent by manually specifying its density of 1060 kg per meter cube and viscosity of 1.8 times 10 to the power of negative 3 kg per meter second based on the manufacturer data at 100 degrees Celsius. Furthermore, a boundary condition is set at the inlet having flow velocity of 3 meter per second. This inlet velocity reflects that fluid is being pushed by the master cylinder and the direction is in the negative Z direction. 4 assumptions were made for this CFD simulation, which we assume the flow to be steady, incompressible, isothermal, and the fluid is Newtonian. Next, our solver type is pressure-based with absolute velocity formulation and steady state. And lastly, for post-processing, a 3D velocity streamline plot was generated by seeding 25 equally spaced points at the inlet. The streamline provides the illustration of direction and magnitude of the flow velocity throughout the orifice opening. As shown in the diagram, we can clearly see that the flow velocity is the highest at the constricted part, which is the orifice, and lowest at the pipe inlet. This simulation is done on 4 different diameters, which are 0.5 mm, 1 mm, 1.5 mm, and lastly 2 mm.
Okay, so let's start with the smaller size, which is 0.5 millimeters in diameter. So the fluid has to squeeze through a very tiny hole, which causes the speed to increase a lot from 0.3 meters per second at the entry to over 25 meters per second at the exit. So this sudden increase in speed causes a big drop in pressure. So because of this, the fluid becomes unstable, and cavitation can also happen, which means the vapor bubbles forms that causes swelling and also uneven flow. Also, since the hose is very small, the fluid takes a longer time to pass through, so this can slow down the braking response. Another problem is blockage. Small holes are easier to get clogged, so it's not very practical for real. Okay, so now let's take a look at the 1 millimeter orifice. So the flow is, as you can see, it's much more balanced compared to the 0.5 millimeters, and the highest speed is around 6.45 meters per second, which is better than before. So the pressure drop is smoother, and that means the system is under less stress. So as you can see here, the flow is more stable, and the streamlines are cleaner, and there's less turbulence. There is still a bit of a swirling, but not as bad as with the smaller hole, because the pressure changes are smaller. So the risk of cavitations is much lower compared to the 0.5 millimeters diameter, which makes the system safer and also long-lasting. Also, the bigger hole is less likely to get blocked, and the braking is more reliable and also faster. So now let's take a look at the 1.5 millimeters diameter.
So for the result of orifice diameter 1.5 mm, the velocity is moderate, which is the peak velocity around 2.84 meter per second. Yeah, it is much lower than 25 meter per second in 0.5 mm orifice. So it will avoid sharp spikes, ensuring smoother and controlled flow. Second, stable pressure distribution. Pressure changes are gradual and steady without sudden surge. So it will reduce mechanical stress, improving component lifespan. The third one is organized flow pattern. The smooth streamline with less turbulence and swirling. So it will maintain predictable, consistent flow behavior. The fourth one, lower cavitation risk. The gentle pressure variations minimize vapor bubble formation. So it will enhance system safety and operational reliability. The fifth one is reliable and practical design. It is less likely to clog than a smaller orifice. It will balance responsiveness, stability, and durability. For the orifice diameter 2 millimeters, the flow is gentle and stable. The velocity range from 0.00228 meter per second to 1.56 meter per second, indicating steady relaxed movement. The streamlines are widely spaced with minimal sharp turns, showing very low turbulence. The second point is consistent pressure behavior. Pressure distribution is stable and gradual, with no sudden changes. Minimize pressure losses, improving system efficiency. The third one is high system efficiency. Energy weightage is reduced due to smoother flow and minimal turbulence. So it will enhance reliability and make system behavior highly predictable. The fifth one, trade-off in response. Braking response may be less sharp due to the smaller pressure drop. So it will potential for a slight delay in system reaction under sudden load changes.
Okay, for possible areas, first is a mesh issue. If the mesh is too rough, it can miss important flow details like turbulence or suppression. And second, material mismatch. We might be not use the same complex materials as in real life, which is affect accuracy. The third Standard properties. We choose to follow SAE standards for simplicity and consistency. Okay, for conclusion, this project analyzed the effect of orifice opening diameter on flow behavior, focusing on velocity and pressure distribution in a hydraulic braking system using CFD simulation. Second, guided by SMART SMART objective, the study simulated orifice size from 0.5 mm to 2.0 mm under fixed boundary condition. The result showed smaller orifice cause higher pressure drop and lower flow velocities, while larger orifice allows motor flow but reduce control sensitivity. Next, an optimum orifice range between 1.0 mm and 1.5 mm was identified, providing stable and efficient braking performance. The project successfully delivered clear, quantifiable data through graph and contour plots, all complete within the set time frame. Next, these findings enhance the understanding of hydraulic brake system behavior and highlights the importance of proper orifice sizing in achieve reliable and responsive braking. Future work may involve real-world testing and transient braking simulation to further validate the results.